So today we're going to take what we learned on Monday and kind of build on it. We kind of talked a little bit about this on Monday, but we're going to go more in depth. So we're going to talk about kinetic molecular theory of matter, also abbreviated as KMT. So whenever I say KMT, I'm saying kinetic molecular theory. All right, so now kinetic molecular theory, KMT, explains the constant motion of gas particles and models ideal gases, meaning perfect gases, meaning gases that are in perfect conditions in their surroundings and atmosphere. So pretty much kinetic molecular theory is there's 6 theories that talk about gas particles. So again, there are 5 points for KMT. And the first point is that gases consist of large number of tiny particles that are far apart relative to size. We kind of saw this on Monday. You saw what the gases look molecularly. The particles are really, really spaced out, and just depends on how big the particles are, relates to how far apart they are. Number 2 is collisions between particles and or a particle and container are elastic, meaning there's no change in kinetic energy, also known as motion. So this point is pretty much saying that once the particles hit each other, they don't combine. They automatically bounce off each other and continue moving at that same speed. So more in depth of this is we have the idea of pressure. Now, pressure is a measure of the force that the gas exerts on the walls of the container, also known as collisions. So when we record pressure of something, we are recording the number of collisions, how powerful the collisions are. And we said that collisions are elastic. They just bounce right off of each other. That produces that pressure we see and measure. So with this idea, now when the number of collisions are higher, so we have a lot more collisions going on, that means the pressure is going to be higher. And the number of collisions decrease, so if we don't have a lot of collisions, they're a really small amount of them, the pressure is going to be lower. Now, point number three is gas particles are always in motion. So they always have kinetic energy. There will never be an instant where gas particles are going to quote unquote bond or connect with other particles or the wall. They're always going to be moving. That means they're always going to be emitting kinetic energy. And kinetic energy is energy of motion. So when something's in motion, they always have some sort of kinetic energy. Number 4 is there are no forces of attraction between the particles, kind of building onto that idea of no attraction, no bonding. These particles will not bond or connect with each other, so that means there's no force of attraction. So if you played with magnets before, and when you put the magnets together, they stay together, but if you turn one of the magnets over, you try to put them together, but they don't. You feel that force in between them. It's kind of like how particles are. Once they touch, they're going to automatically go away from each other, like they're scared of each other. So there's no attraction going on there. They kind of hate each other, if you want to think about it that way. Then number 5 is the temperature of gas depends on the average kinetic energy of its particles. This means that temperature is the measure of average kinetic energy of particles, meaning motion. A lot of you guys think that temperature, you're recording of how hot or how cold something is. That is completely false. Okay? You are not recording how hot or how cold something is. You are recording how fast those particles are moving. Now, heat and cooling is related with the energy. So if something has a higher temperature, the faster the particles. So the faster the particles are moving, the temperature is higher, which means that there's going to be a lot more heat energy in there. That's why we refer to higher temperatures as heating, as hot, because there's a lot of energy to it. But when you record temperature, you're not recording that heat, You're actually recording how fast those particles are moving. Now, if the particles are moving slower, so slower the particles, the temperature is going to be lower. And that's where the idea of cooling is. There's not a lot of heat energy into it, so we refer that as cooling. They're not the same, but they're correlated. So make sure you know that. And number 6, it does not apply to real gases, meaning real world gases. So gases we encounter every single day, because we know we don't live in a perfect world. There's a whole bunch of other factors going into observing different things in the world. So a lot of these don't apply to the actual gases. Something might have changed a little bit. But if we're in the ideal world, the ideal gas laws, gases, that's what we're referring to. All right, so now let's go into the conversation of boiling point. So boiling point of a substance is when the vapor pressure equals the atmospheric pressure of the atmosphere. Meaning the pressure, so when you're boiling water and it starts to boil, it's at its boiling point. It's adding the temperature at which it'll start boiling. So at that point, what is happening is that vapor pressure, the pressure that's being emitted from the liquid into the atmosphere, that pressure needs to be equal to our atmospheric pressure, the pressure of the atmosphere, the pressure of our air, the pressure of what we breathe. Those two have to be equal for a boiling point to happen. Now, it does not always need to be heated. Guys, guess what? Sometimes you don't need to boil water without increasing the heat, having fire. You can boil it so many other ways. And also just more talking about vapor pressure, it's the vaporized particles, meaning particles that's coming from a liquid into a gas. They're colliding on the walls of the container. They're colliding along the walls of your pot, and that produces that vapor pressure. And normal boiling point is the substance ideal boiling point. It's just when the atmospheric pressure equals 1. That doesn't really happen, but if we're in an ideal situation, that will happen. And boiling point, again, depends on pressure, right? There's a lot of collisions going on. For boiling point to happen, that vapor pressure has to equal the atmospheric pressure. So it's very dependent on pressure. Now, if you're lower in altitude, meaning if you are up in the mountains, when you go higher up in the mountains, the altitude, let me rephrase that. Lower altitude, meaning if you dive into a pool or go on the bottom of the ocean, the atmospheric pressure increases. So I don't know if you've experienced this when you're like at a pool or something and you jump in and you touch the ground and your ears start to pop. That is because there's a lot more pressure down there than it is on regular ground. So with that, it's going to, since the atmospheric pressure is higher, it's going to take less time to equalize. That means the boiling point is going to be higher. Okay, so when you're lower in altitude, atmospheric pressure increases, so your boiling point is going to increase. Now, if you're up in the mountains, so altitude's increasing, Mount Everest or in Colorado or on the Appalachian Mountains or the Rocky Mountains, your atmospheric pressure actually decreases. So one of the common deaths when people climb Mount Everest is oxygen poisoning. The oxygen, the gases up there are moving slower. If they're moving slower, there's not a lot of collisions. If there's not a lot of collisions, there's not a lot of pressure. So the oxygen molecules, the air molecules, are moving slower, so it doesn't get to your body as fast as it would when you're on regular sea level. So there's not a lot of pressure. If there's not a lot of pressure, that means the boiling point is going to decrease. Okay, you can boil water a lot faster, right? So now I'm actually going to show you a video of 2 demos I did. One that's pretty cool, that I actually boil water without any fire, no heat. And then I show you the evidence of vapor pressure. So we just talked about boiling point, and boiling point is when the
atmospheric pressure equals to the vapor pressure, so what's being emitted from our liquid. Now, we also talked about that we don't need heat. We don't need a change of temperature for something to boil. So right now I have a beaker of water, just regular old room temperature water in this, I call this the Willy Wonka machine because it sounds like the little train in the Willy Wonka in the Chocolate Factory. But this is a vacuum. So what it is, it's increasing massive pressure inside here. And and as you can start seeing, is it starts bubbles a little bit on here. It's kind of like that simmer when you have water. And soon it's going to get into a roaring bubble. Now, there's no temperature change in here. I'm not putting any heat in here. So when I end this, it's going to still be room temperature inside here. So we'll let this see some little bubbles and stuff on here starting to form. All I'm doing is I'm changing the pressure. It's the same idea for a pressure cooker. Pressure cookers, no heat at all. What's happening is that the pressure in the pressure cooker is increasing, and that's causing whatever the food is to heat up. It's a different word, not the same heat energy we use in science. It's more just a different definition for that word. As you can see, we've got a lot of bubbles, and it's starting to bubble a little bit. Let's see a little bit more. I hope you guys can see those bubbles in there. Here, I can bring it closer. As you can see, we got some bubbles on there. Now, this machine does not work perfect, but as you can see, it starts bubbles right now. We're gonna call that boiling. This machine's very old, so the vacuum isn't as perfect. Oh, but we're getting a lot of boiling. It's kind of boiling right there. Alrighty, so now I'm going to remove, I'm going to turn off the vacuum. I'm going to release the pressure inside it. And when you guys are boiling water for like cooking ramen or mac and cheese, heating noodles, the pot's very hot. So probably you guys are very suspicious right now what's going on. There has to be heat, there has to be temperature. Well, you can't grab the pot, right, when it's pasta because, you're actually putting heat into it. Well, grabbing this, not burning. It's actually very cold. It's actually completely room temperature. Kind of a little bit cold. It's kind of cold in this classroom. So there you go. We were talking about vapor pressure, and we know that vapor pressure is the pressure when a liquid becomes into a gas, and what that gas is, when it collides off the walls, it's producing some pressure. So let's prove that pressure actually exists. So I have this water canister of sorts, has rocks in it for some reason. And I'm going to put some alcohol. It's ethyl alcohol here. No, it's not the alcohol we drink. This is different types of alcohol. And we are going to put that into the bottle. That should be perfect. Then I'm going to seal the top with some parafilm wax. This is pretty much wax. It's easily mendable to cover up any areas to prevent any air to get into. I'm going to just agitate it, and what I'm doing right now is I'm increasing the liquid to become a gas. I'm waiting for it to vaporize. You start seeing the bulge on top. Already you can see some kind of pressure, some kind of gas forming. Sorry guys, that's my phone. Alrighty, we get it. Nice. And I also want you guys to observe how much liquid we have right now, and we're going to compare that to what we're going to have later as well. Alrighty. Let me go ahead and get some tongs. Turn off the lights. And let me get my match switches. Should be right here. Alrighty. Now, let's watch the magic happen. There we go. Alrighty, so let's let that cool down a little bit. So what just happened was I lit the gas, and obviously the fire happened. And if you notice on the bottom, we have a lot more liquid than what we started with. Because remember when we talked about types of reactions? This was a combustion reaction. The alcohol was our organic compound. It reacted with the air, the O2 in the air, and it produced that carbon dioxide, that gas, and the smoke, and a little bit of water in here. So it's obviously it's not pure water. I can't drink this, but it's we have a lot more liquid than what we started with. Alrighty, thanks guys.
Alrighty, so yeah, those were 2 demos. So the first one, again, I boiled water without adding any temperature, any heat to it. It was room temperature the whole time. And again, like I said in that video, it's what pressure cookers do. So if you used a pressure cooker before, know what it is, your parents may have used them before, there was no heat aspect to it like a crock pot. There's no temperature change. What's happening is the pressure inside that pressure cooker is increasing, which cooks your food. And then I proved vapor pressure. When we talked about vapor pressure, that's when those particles, those liquid particles, are becoming into gas. They're exerting a pressure onto that container. Well, I lit that vapor pressure into that container. All right, so moving on. So now we have these 2 terms, evaporization and vaporization. A lot of you guys, particularly on the homework, were using those words thinking they were the same. They are not. They're completely different. Okay. Now, vaporization is a spontaneous process which occurs at the surface of the liquid. Water to steam. When you're boiling water for ramen, it's bubbling, there's still liquid, but there's also steam being produced. Those are your particles leaving from the liquid going into a gas and hitting that surface. Now, evaporation is a phase transition when the liquid phases changes to a gas phase as its boiling point. Like drying of sidewalks in the summer after it rains. It's when it's completely into a gas. So, like I said on Monday, if you ever left some boiling water out, it starts vaporizing. Then when you go, there's no more water anymore. That's because it's all been evaporated. So for something to be evaporated, something to have evaporization, there needs to be some vaporization going on. So they're kind of correlated with each other.